Hello, welcome to Bedroom Builds at the From Python to Rust series, episode 3, Tuples, Arrays, Slices, and Lists or Vectors. Today we will talk about the declaration and basic use of those, and how to access slices of them. Let's jump right into the code. As you can see, we have lots of stuff going on already only for tuples. But let's concentrate first on the first line of the actual code, here and here, to see the first difference in how this actually works. So in Python, it's fairly easy. You just use parentheses. You write your items that you want to have in your tuple. They can be of any type, and you have your many types built tuple. In Rust, it's not that much different actually, because you can use the let statement, your variable name, the parentheses, and the type declaration can be also inferred by the compiler. Here, the A is a single character, so you will probably use U8. And true is a boolean. And for the numbers, if you want to be specific, you can use the unsigned integers and other stuff. And not to forget the semicolon at the end. Very similar. If we continue further down, the indexing is a bit different. So the print looks very similar, as we already know. And here we use the angular brackets to access the items within the tuple. So the first one is with index 0 and the second one is index 1. Same is here, but we use a dot to access the items of a tuple and not the angular brackets like we would in future. We can see that in arrays. Then we can also build tuples of tuples in both cases. Yeah, we again simply use the parentheses and they are built for us. Then here we can use the debug formatter to see the contents of this in Rust. Otherwise, we can also build a simple pair of two items. And here we then actually call our function. And now we will jump on the very top of our code. Here you can see the function definition in Python is just accepting a tuple, returning a tuple. Here we deconstruct the tuple into two variable names, integer and boolean, and then we use them the other way around to then have the pair coming back in the reversed order. And the code in Rust is not that much different. Again, we use the let statement to set up our variable, integer and boolean. We have to use the parentheses here, not like in Python where we can omit this. Then we take the input, our tuple, and this will then fill those variables. And the return, we don't have to note it, as we already know. The last expression is the return. And here we just make the expression of a tuple, and we change the order, boolean, integer, and our return is done. Yep. Then an example for a single element in a tuple. In Python, you would denote this with a comma and with parentheses. And in Rust, the same is needed. So you have your parentheses and you put the comma. If you only put the parentheses, this is just a single element. This will have no consequence. Second example for deconstruction. So we define a tuple, and then to access the elements, we don't have to know their index. We can actually give them names, and then we can use those extra. And last but not least, we can use a named tuple. That's a bit different in both cases. So the named tuple in Python is defined up here, is way more powerful because you can give each and every element already a name. And in this case, it's not very creative. I use the x1, 2, 3, and the 0. I use the name tuple collection to create something called a matrix. Then I can initialize down here the tuple. It's not the same because I don't have the property names, if you want, of my tuple, but I can still create a struct called matrix, but that doesn't hold the named properties, but only a tuple of those 4 numbers. And to make the declaration, I just use the matrix struct name, give it the values that I want to, and then I can print it. Running the code, let's do Python first. this means Python runs this with Python tuples, and we can see our output. It, as predicted, only gives us a single normal integer and not the tuple if we don't use the comma. Remember this from here. And all the other things are fairly self-explanatory also. Good. Let's jump over to Rust. That means I have to do this one. And compile this first, of course. So we use the Rust compiler again, tuples rs, and then we run tuples. And one of the major things is how to not declare a tuple is not forgetting about the comma. All the other things, here we have the reverse pair coming in 1 true, true 1, our nested one, and our matrix is also printed out nicely. This would be the big difference, I guess, that the named tuple is way more powerful than this structure, but it's not the same, but kind of similar from the idea. Let's go back to our code and swap over to the next examples of arrays. And this means that we are discussing a big difference, mainly that arrays in Python are not really used, especially not the default implementation that comes with the standard library of Python. And arrays in Rust and Python have a very different way of how they actually work. The main difference being that every declaration that you do as an array in Rust is something that the compiler knows, puts basically into your binary, and this is then also getting its own separate space on the stack. And this way you avoid memory allocations. And this can be useful if you write for a system that doesn't have a memory allocator, for example, some embedded stuff. Or if you really want to know and be sure that this is a static information that you're bringing with your program. In Python, that's not so much the case. It's interpreted. And even this creation of an array is using a temporary created vector, basically, that then makes an array out of this. They are, however, more efficient because they have a data type and they are really very strict and can be much faster for computations. This is then, of course, used by those scientific libraries like NumPy that use the faster data storage. So what happens on the left here is I first import the array type because it's not commonly used. And then you would have to declare the type of your integers and then something that gives you the values that you want. Below here you can already see in my comment that this is not smart to do, but you can get a 500 element array filled with zeros of the type unsigned integer 64 bits like this. It is much smarter and easier to read and more performant to use NumPy zeros in this case. And however, this is what you can do. Accessing the elements is again with the angular brackets, first and second element. To get the length of it, we use the len function provided by the Python engine. And to get a slice, the common known operator is the colon within the angular brackets. And at the very end, we try to print something that is out of bounds. And let's see what happens. Same thing as always on the right side here in Rust. We declare an array. Here we declare an array with 500 elements of 0 and also a data type. I have done the same thing below. So here I use a different data type, but you can write it like this. So the actual type declaration with the colon and the angular brackets is superfluous. Again, access first, second element. This time we have the very same code, angular brackets and accessing 0 first. And 1 is accessing a second element. You get the length by using dot and then the length function. To then borrow, this is important because you cannot access a slice without borrowing. You need to use the ampersand. This means you are not directly the owner of this data. You're only borrowing access looking into the data that is within this slice. The denotation here is 2 dots. It's not a colon like in Python. And you get the same numbers though, so you just use the 1 and the 3 to get the same slice as if you would here on the left side in Python. And then on the bottom we also try to access an element that actually doesn't exist in the array. Okay, let's run this code. Let's see what happens. We have already prepared our Python thing. Let's clear. We run Python arrays and we get our input that works fairly fine. We have first element, second element makes sense. Then the sizes, and here we get our slice. So the numbers 2 and 3 are printed. So this takes the slice from the second all the way, not including the fourth element. So in this case, it is 2 and 3. And then it dies on us, accessing out of bounds. So the index number 5 does not exist. And with an index error, this is how Python treats that. Let's see how Rust does that. We swap back to see our Rust code. Here we have our Rust code. We cleared it as well. As usual, we compile it. And this is Rust, and it knows about the arrays. As I said before, the compiler knows about all the arrays, their size, and puts them into the binary. So he knows also that this array does not have index number 5 accessible. So it tells us that index is out of bounds on compilation time. We cannot even compile this program. We have to get rid of this line in the code, which I'll do now. Now this compiles and it runs and shows us also the slice with our 2 and 3. So that is equivalent with the big difference that we cannot access arrays out of bounds. Let's keep going quickly to the vectors. This means going back to the code, of course. So let's swap the pane, edit vectors, no, lists, of course, because it's in Python, it's a list. And here we have called it vectors because they are vectors. And let's move to the top in both pages. And we can continue with our vectors. Let's move to the top. And we see here declaration of a list in Python is very easy. Use angular brackets, you put your elements inside, and it's done. Not too crazy in Rust either, so let again, of course. Then mute is important because we need to be able to mutate our vector later on in the code. Then we use this macro that is very helpful called vec. Then again, the angular brackets are values, and if we want to be fancy, we can also put a type declaration here. And later on, we get to add an element. So we push the number 4 to the vector. This is done with the push method. And on the left side, this is done with the append method. So there's a slight naming difference, but the effect is the same. We added the number 4 to our list or vector. Then the length is, again, here a method, and here it's a global function. Then the second element is accessed again by the index 1 using angular brackets in both cases. To get the last element, we can use pop in both cases. It's called with the same method name. Then the fourth element is accessed with this, just to verify that our operations that we've done had the consequences that we expected. And here we are printing the contents of it with a separate line for every element. And this is very easy in Python. You just do for your variable name in your list, and then you can use this x that you've defined here in the for loop to print, for example. Same we can do in Rust, and it looks very, very similar actually, because we use also the same syntax, except for the added curly braces to denote the code block, and of course the semicolon for the print, but otherwise this is not too much different. Okay, let's run this code, first the Python version, and we can simply use Python listspy, and we can see that it works fine and all the stuff that we already know about is done as expected. However, it also has the index error again, accessing the element 3 of this list, which doesn't exist. Now let's compare that directly with the Rust code. So we would have to compile the vectors code first, and it compiles fine. So even though, remember, we have the access out of bounds into our vector here, this time it compiles though, because it's all dynamic. So at runtime, Rust cannot predict the size of our vector. However, it panics and dies on us, as does Python. So the index is out of bounds, as you can see here. And because the same problem, we try to access the index number 3. And the whole length is only 3. The rest is more or less the same. Now, let's go back to the code. And let's see. This means we have to get rid of the out of bounds access. That is down here. And we also need to get rid of this on the other code. Okay, code is reformatted, sorry. We removed the excess out of bounds, and we will quickly see the big changes that come up and out of this. The loop that we spoke about before, that will print our elements, is the next topic. So let's jump into our Rust pane and compile our code for the vectors. And we can't, because the borrow checker doesn't like what we are doing. What is happening here? We are trying to loop, and before it compiled fine, and it would have worked as well. We are trying to loop over XS, and now the compiler is complaining that we moved the variable or the contents of XS, the vector, out. And now later down the code, we try to use it again, borrowed here after move. So in Rust, it is enforced that there's only one owner of the data, and only this one owner has access to it. If another one wants to have access, he can only borrow it, or in the case of moved, you can move it to yourself, but then you are the new owner, and you would have to make sure that the others below your level would borrow it. This is not the case in our code, so Rust does not let us compile that. So this easy way of writing a loop for x in XS works, but only for easy cases. If you want to do more with this vector than just print it out in multiple lines, you will have to make sure that the compiler is helped with information of what you want to do. So borrowing is done with the ampersand. So you can write this code. This is, however, not very clear. It is much smarter to use the iter method that would generate an iterator that borrows the elements out of this vector. And in the comment below, you can see that I noted that you should borrow and not use into iter. So the code that we had before that only showed the XS, the loop that actually works, is desugaring into an into iter code, which moves the ownership to X in every loop iteration, which is fine if we really only want to print it, but that's not clever because here we only want to read the contents of the vector. We do not want to modify it. We have no real reason to be the owner of the elements inside of this. So we should only use borrowed references, which is done by the normal iter method, and this gives an iterator that gives us borrowed elements. So now this will work fine. Let's save and see if it's true. Let's clear before we run the compiler again. Now the compiler is happy. Now we can run the vectors code, and we get to have our output of 1, 2, 3 in this funny formatting that we chose. Let's go back to the Python code and we check out how this all works compared code-wise now. I tried to make the same code if you want on both sides. So here we have our loop that we had before for the print. We fixed it to be compilable again, to only borrow. And here we have another loop that does enumerate every index of the list. And here we get a tuple that has the index and the value. And here we can print it this way. Okay, as we can see on the first loop, we used this borrow iterator already. We use this one here again, but this time we feed it into another iterator called enumerate. This one takes those references, adds the index, and returns a tuple of index and value. Since we are dealing with a tuple, we have to tell the compiler that it is expecting one, so we use the parentheses. And then we can print it the same way as we do here in Python. We get the index and the value printed. And below, we use yet another type of iterating. So we already had the into iter that was done for us implicitly. That would move the ownership. Then we have the borrowed references. And here we get also a borrowed reference, but this time it is a mutable reference. This means we can mutate directly inside the vector. This is very efficient because we don't initialize new memory or whatever. We modify the existing element inside the vector. For this, we have to dereference with the star operator, our borrowed reference. Then we do our operation. In this case, we multiply it by 3. And after this, we have already a modified computation stored in our vector. And this is the code that does the same in Python. It works, however, differently because as far as I know, you do not have an easy way to access directly with an in loop the elements of primitive value list. Then what you have to do is use the index that you got from your enumerate and use it as the accessor and do your computation. And however, almost nobody writes it this way. If you wanted to multiply something by 3, you would use a list expression, and this is done here. However, this kind of creates a new list based on this list with the multiply by 3. And the same code in one line, and actually also doing a allocation and creating a new vector is written here. This is very advanced. We have not yet spoken about most of this stuff. So I already just used iterators just like that, which is done here. Then I use a map function that takes a closure that then does the multiplication. Then we collect the thing into the defined vector here. And then we would still have a one-liner that can do all of this for us. This up here can also be written as a one-liner, but that's an exercise for the viewer. Then at the very end, we can also create the vectors from ranges. So range is denoted by parentheses, start value, 2 dots, and end value, closed by the parentheses. And then you can collect, because this generates an iterator, you can collect it into a vector, and then you have your vector. A similar thing in Python would be also, again, a list expression, where you would use your range function, giving you an iterator over this range, and you run it and create a vector from it. Let's run the code to see if it does what we expect it to do. And we did already for Rust. And you can see here that we multiplied by 3 2 times. So we did 1 times 3 is 3 times 3 is 9. And the other values, that is self-explanatory. So here you can see the proof that we did the 3 multiplication here and here again. Let's jump back to our Python code to verify that what we've done really works. So now we run again Python lists, and we have the same output as expected. We have 2 times multiplied by 3, same output, and when we collect our range we get this output as well. Okay, let me quickly jump back into the code again. I hope this introduction into tuples, arrays, lists and vectors was useful. Thanks for watching. Coming up next in the From Python to Rust series, it will be strings.